Hi, my name is Akshat, and this is day one of 30 days of machine learning. So this is going to be a quick explanation, come walkthrough, and I have already included the GitHub repo link, the dataset link, and any other small detail in the description itself, so you can go and check it out. And without wasting any time, we will move on to the model straight away. So today, on day one itself, have approached to build one of the most important fundamental and classical models, classical problems in machine learning, customer churn prediction. So, for this, I utilize the Telco Customer Churn dataset. This is the dataset available in CSV file. Don't worry, I put the download link in the description itself. The shape of the data, we'll be getting to everything soon. It is a massive data set which has 21 features, 20 which are going to be the independent feature, and the 21st feature, the churn feature, is the one that we have to predict in this U column right here. So, first things first, getting to the problem, customer churn. So, if we take any example of a subscription-based service, it can be Netflix, it can be your phone bill, it can be a SaaS platform, it can be your monthly chat GPT subscription, it can be Airtel, Vodafone, Verizon, whatever bills you pay monthly. So there is always a risk that we as the customer might leave their service, right? Us leaving their service basically costs business loss to the organization in question, right? What happens is that customers are not that easily replaceable, contrary to popular belief. Getting in a new customer is 5 to 7 times more expensive to the company than keeping an older one, which is why it becomes vital for all of these telecom companies and all of the organizations in question to try and keep as many customers as they can, whilst also predict a rough estimate of the customers that might leave. Specifically speaking, the customers who leave are called as the customers which churn. The customers who stay with the company for a longer period of time are called as the non-churners, and the customers who leave are called as the churners. Okay. Our goal in this problem here today is very simple. We have to try and provide a rough estimation of the number of customers that might churn, specifically based on this data set. This is the telecom data set. Okay. So these are all the features. Again, there is no point of going through this data set manually. Okay. It's a massive data set. If we want to get into the specifics, I have included this right here. We have got the data set right here, the telco customer data set. And, uh, this is the shape of the data set, 7,053 samples. So of course, no one can go through it manually, which is why our approach is pretty simple to go and have an EDA pipeline, an exploratory data analysis pipeline, which brings me eventually to the code. So this is the code, pretty simple, nothing too complicated. These are all the standard imports, pandas, numpy, uh, Seaborn and Matplotlib for the visualization part. Fine. This is something new that I've started adding recently to the machine learning pipeline, and I'll be explaining it shortly. These are all the classical, sklearn library imports. We have got logistic regression, which is the initial model that we have used there, and I'll be explaining as to why we have done that. So these are all the accuracy and other classification metrics, the classical metrics that we use in the model. First of all, we load the dataset pretty simple. This is the dataset right here. I copy the paths and I upload it right here in order to, basically keep the dataset stored here. And this is temporary. So in order to have this as permanent here, we can save it to a Google Drive. But that's again a thing of the future. So here we have got the EDA pipeline. This will print the shape of the dataset. I've commented all of this out because this was for me specifically. It served no purpose in training the model, which is why I have included the visualizations separately right here. Okay. So if we go to the EDA, we can really see that, you know, wait a second, that we can really go and see through the visualization part of it, about the shape of the data set and basically going through it. We have got this df dot describe. This is again very typical. It gives us a summary statistic of each of the samples. You can try it out, but this is all for your personal use so that you can, really learn about the data set pretty well because again, there is no point of manually going through a massive data set. This is a very important pre-processing technique or EDA technique. This returns the sum of all null values of all the samples, all the features in the data set. And this data set, it didn't have many, missing values, but I think it had three features where the values were missing. So we have all this, the basic EDA part. We have an idea of the data set, an idea of how the data set looks like, what is the spread of the data set, all of these things. We move on to the data pre-processing pipeline, which is basically the work of a data scientist in the entire pipeline. So, if we look at this data set, we have got this customer ID right there. Okay. It's like, employee ID or roll number for a student. Now, does this help in any sort of prediction or classification? No. No. Answer is no, straight away. Why? Because it is a unique feature. It is like a unique key in a database. It is just used to have an idea about each of the entries. It is not going to predict anything. So what do? We remove it using what? df.graph. Very simple. This is all basic, fundamental Python. Then this is again very important. So total, this is again a trickery in the data set that these people do. I don't know why. Total charges are supposed to be an integer, right? Like this value, where is it? Total charges. Let me see this total charges. This is supposed to be an integer right here. This 29, 1889, but these are actually string values. You can try it out yourself, but these will actually be string values. And if I try to print these string values or use these string values by assuming that they're integers, there's going to be an error. We don't want that, which is why we converted it to a numeric value. And if it is giving us an error, it will print that column as empty. This is the good thing to do here. Again, we have got total charges, so we have got some missing values in total charges, which we fill using the median. Why the median? It is not sensitive to outliers. It gives us the middle value. Okay. Very simple. Then we have to do the encoding. Basically, we have got customers who churn and customers who don't churn. So, this is right here. Churn, no or yes. And the machine doesn't understand no or yes. So we go on and encode it as 0 and 1. Again, very typical. Df cd.get dummies. Again, very simple. This basically encodes the entire, data set as numerical values. So this is very important for the data pre-processing. Then we have to define the features, independent and dependent features. Like I said, churn is the dependent feature. We are predicting it. Rest 20 features in the model are used to predict the value of churn. So those are the independent features. We make the train test split. Standard X5 test size is zero point 0.2, which means 20%. It's a classic 50-20 split between training and testing. This again, pretty classical thing right here. This reminds me. Random state is equal to 42. This is basically for result reproducibility. See, whenever the model is trained, the model tries to use a different part of the data set every time. But we want the results to be somewhat uniform. And so we use this random state is equal to 42. Now, why 42? Entist did it. I don't know why. Okay. Now, coming on to the main question, the model. Okay. So why logistic regression? Why not naive Bayes? Why not some other model there? Which is a very good question, to be honest. So if we look at our problem, which is churn prediction, 0 or 1, we have to decide whether the customer is staying, whether the customer is leaving. 1, 0. What does that tell us? Binary. We can basically conclude to the fact that it is a binary classification problem. And so our eventual goal is to find a model that fits through those values very well. Now, the number one model, at least the baseline model that comes to my mind for this problem, is going to be definitely the logistic regression model. So I have included the math intuition in this as to how to think to approach this problem so that we know by a definite chance that logistic regression is the correct fit here. So I have included this here. This is basically the backend or the working of the logistic regression model. So it utilizes the sigmoid function. This is the same sigmoid which is used in deep learning activation functions. So this value is what it calculates, 1 over 1 plus e to the power minus z, whereas z is nothing but the weighted sum of the feature and the model weights, and the bias is added to it. So this calculates values between 0 and 1, basically probability values. Okay. So for all the features, I'm going to calculate this sigma z right here. Okay. And I'm going to get some values. Now, what do? I basically, introduce a split in it or a decision rule. I say that, okay, if the probability values are greater than zero point 0.5, it means that the customer is going to churn. The customer is going to leave. Okay. Else the customer is not going to leave. Why zero point 0.5? 0.5 lies exactly between 0 and 1, so it gives us the chance to have a very safe model in place. Okay. Whereas we could also go for higher values, such as zero point 0.6 or 7, that would make the model a bit more strict. But in this case, I got pretty good results by using zero point 0.5. Okay. So that is the intuition about, logistic regression. Now, scaling is again pretty important here. We have got features having different uh, values altogether, right? We have got these monthly charges, we have got total charges, then these values, which is to be predicted, these are encoded. Payment methods are encoded. This is encoded. So in the end, our feature scale is pretty different and we want it to be uniform. So how do we make it uniform? By using standard scaling. Standard scalar in the backend, it applies the statistical formula x minus mu divided by sigma. Mu is the mean of the data set, sigma is the standard deviation of the data set. After applying this formula on the entirety of the data set, the mean becomes as 0 and the standard deviation becomes as 1. So the model has a more uniform representation rather than the one it had before where every feature had, different scales. So now the model is more uniform. Okay. Then the training testing split, pretty simple. This is again something that my professor says too much upon. The scalar dot fit transform and scalar dot transform difference. So dot fit transform means that the scaling formula will be applied on the training data set, and the mean and the standard deviation values will be learned. Whereas for the testing, we are not going to actually calculate the mean and standard deviation. Now, why is that? Think about it. If we calculate the mean and standard deviation for the testing data set, it means that it basically loses all the point. The point of keeping the testing data set is so that it is hidden. It is validation data, right? You cannot show validation data. But if you calculate the mean and deviation, you are basically causing data leakage. So there is no point of training the model on the testing data set once you have fit on that data set, which is why we do not fit on the testing data ever. See, this is just transform. Now, one new thing that I started to do. So in real life machine learning models, there are two statistics that become very important. One is the training time, or basically the prediction time, and the other is the inference latency. They are quite similar. Training time represents the total time used to train all the models, combining all the epochs throughout. It is just very useful to have a good idea as to, what time we are dealing with in solving the model. And, similarly, we have got the inference latency, which is time taken by the model per sample. So total training time divided by n. N is the number of samples, is how we get the inference latency. Okay. So I've calculated the inference latency for the model as well. Then comes the juice of the model, the classifier. I've taken it as CLF, but usually conventions say that this should be MODEL model because that is how everyone identifies it. You can do that. These are the max iterations. This is very important. This means that after 1,000 iterations, my model will stop running. This basically prevents overfitting, and given the size of the data set, 1,000 iterations are enough to get an accurate reading. Solver is equal to LBFGS. This is kind of unnecessary, but I really wanted to stress upon it. So if you allow me to look here, if I read from my notes, LBFGS means limited memory Broyden Fletcher Gold, Farb, Shano. Now, no need to memorize that. What is that actually? See, this is one very important mathematical fact about logistic regression. So, logistic regression doesn't have a closed form solution. What does that mean? It means that logistic regression doesn't really give you like an answer or a value. Okay, you rather have the log loss entropy or the binary cross entropy as the loss function, which you have to try and minimize. So this solver LBFGS is used as a solver to minimize that loss function. If this solver is taken away from there, it would result in no changes. Why? Because when we train a logistic regression model, the LBFGS is a solver by default. Okay. And if we again don't specify the max iterations here, the max iterations are 100 by default. So this is pretty good. Then we train the model by fitting it on the training data, X train and Y train and 80-20 split. We then, this is end train, basically the ending time at which the model stops training. This is useful to calculate the training time that we want. All right. So again, one more small optimization. So this is important. Cross validation, again, it's a pretty well-known concept. So, we have got an 80-20 split, but the model can choose 80% from anywhere in the entire data set, right? Let me show you what do I mean. So this is the data set. Now it has got 4,000 something samples. So 80% would mean what? 320 something samples, right? So let's say I take first 320 rows and rest of them I keep them as training rows. And this much I keep them as testing rows. But what about I skip some entries? I go here and then I take from this entry right here until all the way down is my 80% and then the top is my 20%. The results here would be different, which is good because we want different areas of the data set to be used in building the model. And as the result, we want the mean or the average of all of them in order to have a brilliant idea about the accuracy. That is exactly what we have. We have taken five splits, so it will be taking, an 80-20 split from five different parts of the data set and then averaging them to give us a very good answer. This is the inference latency measurement, pretty simple. Like I said, the training time, which we calculated using this, divided by the number of samples, which is going to be n. In this case, I've not really taken n, it is a length, simple as that. Okay. Now, coming on to one of the most important parts in the entire module, let me just open the repo once again. So since this is a classification model, we have got confusion matrix, we have got accuracy, precision, recall, F1 score. We have got all these amazing statistics. Now the thing is, do we need all statistics? The answer is no. So I'll be explaining as to, very simple thing as to why accuracy becomes a useless statistic here. Tell me something. When we are predicting customer churn, what do we want? Let's say I'm part of an organization. What do I want as the member of the organization? I want more customers to be predicted less correctly, right? I want that, I get an accurate idea that, okay, in the month of December, 20 customers are going to churn. So you should start calling them up and, really offering them some deal or some discount that, so that they don't churn, so that the company doesn't face the losses and that business profit is maximized, right? Now, let's say churn data set has 80% as churners and 20% as non-churners. What do I mean? Okay, I mean that these values, these no, 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 yes values. So I have 80% of no values and 20% of yes values. Now, if I take a random part of the data set, I get an 50% accuracy. But is that number 80% of any use to me? Absolutely not. Because it is saying an 80% accuracy, but it is not really predicting anything for me. It is acting like a dumb model. This is where recall and precision come in. They are, like the big daddy of statistics and classification models. Why? What is the mathematical formula of recall? Or better yet, let's think this in terms of errors. Let's say that my model predicts that 20 customers are not going to churn, or it rather says that let's say five customers are going to churn. But in reality, 15 of them churn. Okay. So what happened there? N values the model predicted as false negatives. So what's going to happen? Nothing. N values are predicted wrongly, which means that the organization faces the loss for those 10 customers. That is extremely costly. That is one type of error that, a model can make. The other type, let's say I go on and say, I have a good model. It tells me, okay, 25 customers are going to churn. Now, in reality, only five customers churn. So what about those rest 20? They were false positive values. Now, how are false positive values going to hurt? See, what happens is that once the organization gets an idea that customers are going to churn, they go and start calling up the customers or offering them deals. So they'll be calling them up saying, we are offering you, these many calls and this much data for this and this money because they don't want the customers to churn. So this wrong values, false positives also lead to a waste in business resources for the organization. Okay. The precision basically will be responsible for the false positive values because we want the precision value to be basically as high as possible. Because the more false positives are there, precision is going to go low. It's going to go very low. We want it to be high. Okay. Let me open up the confusion matrix. See, this is the confusion matrix. Predicted versus actual values. This is all in the repo. You can go and look at it. Okay. This is again describing the statistics once again. This is pretty basic. See, recall is going to be ability to detect churn customers, which is why it is the most important. Precision is the correct churn predictions, which means we don't want false positive. We want both of these values to be as high as possible. Because if these values are low, it is going to lead to horrible model really. Okay. So we want a good value. Nothing when we go on and we print the statistics. One very important new thing that I started doing again, failure case analysis. See, we can go through every model theoretically, but there is no point unless we evaluate where the model missed, right? Where the model misclassified through the data. All right. So that is precisely what we do here, the failure case analysis. This is again something new that I don't didn't used to do before. I started this now. So failure case analysis again is going to tell us the places where the model might fail. See, as an engineer, it is very important to know where the model might break when it is scaled or when data becomes too messy to handle, right? So customers, again, this is something I observed. Customers with a similar tenure and billing patterns. Let's say that in the dataset, customers have got similar values for total charges and payment, but one of them doesn't churn and one of them churns. So the model is kind of surprised that these two customers had similar values, but why is one of them churning and one of them not? Not. Okay. Then, very important, logistic regression, like I said, it is mathematical and it is very fast because it's just involved mathematical calculations. So if non-linear relationships are involved, it cannot handle them very well. Okay. And like I said, that we need good encoding and feature scaling. So if, we had 20 features right now, let's say what if we had 40? What if we had 60? Heavier and heavier EDA. We have to take care more about the pre-processing part. We cannot even start building the model. That is very important. So this was pretty simple. And this is another experiment that I tried to do. You can, look at it. It was pretty simple. Uh, Basically, we evaluated the training time while taking different proportions of the data set. The point was similar that, different, that we tried to notice as to how the training time increases with the number of iterations or the size of the data set with logistic regression. There is also a graph to evaluate this exactly. Just give me a second. This is bringing us close to the end. Okay. Confusion matrix, proceed curve. What else do we have here? Feature importance. This is the training time scaling. See, initially what happens is that as the data is increased, the model accuracy and the training time both increase. Then it takes a sharp drop right here. This is again specifically due to the computer training, not due to the theoretical values. And this is what happens. Um, yeah. This is again the ROC curve, very important. ROC curve is the receiving operator characteristics curve. It plots the true positive rate versus the false positive rate. So this value should be as close to 1 as possible, as high as possible. 1 is the maximum value it can have. Zero point 0.5 means that it is a randomly guessing model, and 0 just means that the model is worthless. So we got a pretty good value right here. You can again look at this. Okay. Uh, One good thing we did, feature importance. So we plotted a bar graph visualizing which features contribute the most to predicting whether the customer is going to churn. So this is the importance. So we can see that internet service, total charges, and whether the person is streaming or not. These three were the most important factors, most influential factors in deciding whether the customer is going to churn or not. So that is the fact about it. Last two things, again, the model is pretty much done, which we usually skip, but this is, I think, pretty important. The time complexity. Okay. So how do we do it? How is the time complexity calculated? See, here the time complexity is less about the for loops or the functions and more about as to what the model is doing. Right. So what are we doing in the model? We are calculating a weighted sum, right? What weighted sum am I talking about? We are calculating this sum basically, right? The W is the model weight and multiplied by X, which are the features. And W is, of course, W of T means a transform matrix because we cannot multiply W and X because their shape was the same, right? You cannot multiply two such matrices. And D is the bias, which is added to it. Now, for n samples and d features, when you multiply n samples, which means that n weights and d features, which means x, so you really get rough and about an n into d type of time complexity, okay, which means a big O of n into d complexity. In a lot of theoretical texts, it is given as a big O of n, right? Because n is a lot larger than d usually. In our case as well, you see, d is nothing but these features right here: customer, gender, senior city, partner. How many are these? There are 21. Okay. And n is the sample size. What is the sample size? More than 4,000. 4,020. Okay, so 4,000 is way massive, which is why a lot of times this D is ignored right here. And you can just write big of N as. So this was it for the customer churn prediction model. Again, a very important model that people usually skip. It is very important for the two fundamentals. You can check out the code and all the visualizations from here. I have included the link of everything in the description. And thank you so much. We'll meet on day two with the customer risk prediction model. Thank you.